The graphs of y equals f dashed x and y equals f double dashed x of a function y equals f of x are shown below. The function y equals f of x passes through the points 1, 4, 3, negative 2, and 5, 1. Determine the coordinates of the maximum and minimum points of y equals f of x. Well, we know that at these turning points f dashed x will be 0, so we can see that happens here and here. And let's not worry about this one just yet. So, when x equals 1, we can see that the second derivative is negative. And that indicates a maximum. So we've got a maximum at 1, 4. When x equals 3, the second derivative is positive. It's above the x-axis. So the second derivative being positive indicates a minimum. And when x is 3, we can see that our original curve goes through 3, negative 2. So that's at 3, negative 2. Determine whether there exists a horizontal point of inflection and give reasons. And that's where we start looking at this one here. We can see that the gradient is 0 here, and since this is the gradient function, we can see that we've got a positive gradient because it's above the x-axis, then 0, then positive. So positive, 0, positive is a point of inflection. So yes, and we can see that that's at 5, 1. And then we need to give reasons, and we can say f dashed x goes positive, 0, positive, and that's enough. I might draw the little sketch that I've got above as well. In the mark scheme, they also say that you can say the second derivative here is 0. I don't really like that because you can have minimums where both f dashed x is equal to 0 and f dash double dashed x is 0. For example, on the curve of y equals x to the 4, you have a minimum just here, and both the first and second derivative are 0 at that point. So I don't really like that second explanation, but they would accept it.